Okay, so welcome everybody. Our next speaker is Maxim Chernodub, who's currently in Tours, France, and who will talk about the scale anomaly, non-quantized edge currents, and direct measurement of the beta function in Dirac semimetals. So Maxim, the floor is yours. And you need to unmute.
Yes, sorry.
Now we can hear you.
There was some different slide, but really different. So Andy, thank you very much for inviting me to this very nice conference or nice workshop. I enjoyed it very much. And I'm just would like to give a talk about scale anomaly, about boundaries, which I call H here, and quantized edge currents, and the beta functions, which can be measured in Dirac semimetals. So as far as I understand, I have like approximately 40 minutes for a talk. So yeah, just in case, please ask me questions, because I will be working between two areas, between condensed matter and or I would like to say better solid states and the field theory. So this talk will be in between the two. So please don't hesitate me to ask questions here. Oh, just one second. Yeah, so first of all, let me start from the integer quantum Hall effect, which is very well known for its quantization of the Hall conductance. So basically, the typical Hall setup, I will mention very briefly, is the following. So we have some, say, plate to the two-dimensional conducting material. Then we have a transverse magnetic field, such a way that the carriers of charge, electrons or holes, they move in circular orbits. And if the material is ultra clean, so we have no impurities inside, then basically we will have a strong enough magnetic field. We will have that electrons will move only around the cycle boundaries, and those who are at the edges will travel, one of them will travel in one direction, other one travel in another one direction. So this will be semi-classical skipping orbits, and basically this is one electron phenomenon. So for electrons will sit at lowest Landau level, or it's a series of Landau levels, and when we increase magnetic field, then those relation levels will change, and the number of electrons which go along the boundaries will also change. And that's why this is just discrete phenomena, which very well defined, very well quantized, and therefore the conductivity which is so-called transversal Hall conductivity, which is perpendicular to applied magnetic field and applied electric field, if you put it in this direction. So we will get that currents in net current in that direction, because the population of electrons at two sides will be different. This conductivity is very well quantized, and this number nu is integer. So E is electric charge, A is a Planck constant. It's integer, and it's very well known. So it's very well quantized in the sense that it's one of the most precisely measured quantities in physics. It's known up to 10⁻⁻10 precision. So it's extremely very good. And this number is, yeah, so it's a very this number can be used to measure, for example, electric charge, say. Okay, and the question is that if we have the scale anomaly, then this number will become no more quantized. So we'll get some correction to that. And I would like to discuss in particular this effect in this talk, because the scale anomaly can induce non-quantized current along the boundaries. And those non-quantized currents can presumably be measured, probably, in the so-called Dirac semimetals. So what are Dirac semimetals? Here I introduce generic semimetal, which is vile. It's the following. So we have a material, which is a tabletop, so it can be done in tabletop experiment. So we have some material. This material, in this case, it's just one of them, shown here. So there are many of them, different ones, and they were discovered, say, approximately 6-7 years ago, even earlier, maybe, depends on how to look exactly. Yeah, and typically the materials, they have quite complicated electronic spectrum. So everything here will be about electronic spectrum close to Fermi surface, because the electronic spectrum, which is important for the measurement of conducting properties, for transport properties, either thermal or electronic one, is those electrons which live close to Fermi surface. And it turns out that despite of these very complicated energy levels, electronic levels, electronic bonds, those bonds which are close to Fermi surface have interesting features. They have some crossings. Those crossings are topologically protected, and in 3 dimensions, those crossings they form cones. So for those materials, for example, here, this particular example, this is this violet type semimetal. So there are two cones which are separated in space. In this case, this space is the momentum space. So we have Brilliant zone, we have some particular part, for example, either there or there, of LNG levels, which are crossing each other in the cones. And those cones, they are associated with left-handed and right-handed quasi-particles, which propagate as if they are real relativistic fermions. So basically, those materials offer us some specific version of the standard model. In this case, the standard model will be broken in the Lorentz sense because the velocity of electrons is different, and also there is some distance between left and right-handed cones. But still, we will have some particles which are propagating with propagating basically with their own velocity of light. So they will have the gapless or massless energy spectrum. Okay, and those cones in general, so here again, for beauty, I just here show the violet metal. So this is momentum space, horizontally and vertical axis matches the energy space. Again, for violet metal, in general formulation, one can formulate the theory in terms of some Lorentz broken Dirac system. So we have in covariant formulation in quantum field theory, one has just this simplest description of the massless electrodynamics. So basically, we'll have Dirac fermions with interacting with minimal sense long derivatives and dynamical gauge field as well. In the Dirac semimetals case, which those cones are superimposed to each other, in those cases we will have basically the same theory. The only problem here, the only difference here will be that the part which describes interaction between, which describes the special propagation of the electrons is preceded by Fermi velocity, which approximately 300 times smaller than velocity of light. That's the one difference. On the other hand, this is typical relativistic system, and so lower energy properties can be described by the Dirac Lagrangian. That's all, modulo the Lorentz broken terms, which are under control. And again, that's what I repeated again. So we have two types of semimetals, Dirac semimetals, which where cones, left-handed cones and right-hand cones live in different sides of the Brilliant zone, and also Dirac semimetals where those cones are superimposed to each other. So this type of semimetals is, of course, closer to the standard model of particle physics. And I would say it's less broken in terms of Lorentz invariance, but still the Fermi velocity of the propagation of those particles differs from velocity of light. That's an important issue as well. Okay, but it will not be important for the topics which we will discuss below. And those models, they have classical symmetries. Again, let's look to the Dirac fermion, say consider one single copy with zero mass, and consider the symmetries. So symmetries are very well known. We have a vector symmetry, which corresponds to conservation of electric charge. We have axial symmetry, which corresponds to the conservation of axial or chiral charge, which is classically conserved. And we also have here scale symmetry, because the theory has no massive parameter, and that's why we can rescale all quantities, including distances, fields, according to their canonical dimensions. And the corresponding current, which is conserved, we very well know, is a dilatation current, which is given by conservation of which is given basically by trace of energy momentum tensor, which is again classically is identically zero. Okay, we have symmetries, and we have, of course, anomalies. Anomalies, they break those symmetries. The vector symmetry is untouched. It's a holy thing, because a vector, we know that vector symmetry corresponds to conservation of electric current, which is a conserved experiment. But we have also zoo of other anomalies. There are many of them. There are 6 different triangles in this model, if you don't even include torsion in this theory. Those which are popular, which are discussed often, these are axial anomalies, AVV type of anomalies. There are mixed axial gravitational anomalies, which describe coupling of axial current to the graviton. And the one which we will discuss in this talk is different anomaly, which is conformal anomaly. Now, this anomaly, or it's called different conformal or scale anomaly, better probably to call here scale anomaly. So this anomaly corresponds to TVV vertex, which says that if we consider dilatation current, if we just consider conservation dilatation current, it will not be conservatively proportional to T alpha alpha, which is classically is 0. But on the quantum level, the energy momentum tensor, trace of energy momentum tensor is non-zero, and it's proportional to beta function. Again, here I discuss, I did not mention that, I discuss here flat background. So here in this particular work, we don't discuss any corrections which come from the gravitational part of the anomaly. We don't consider that at all. Okay, so this is conformal anomaly. It's not so beautiful like axial and mixed anomalies because it's not one loop exact. It has no topological reason between them. I mean, topological reasons that it's beautifully, I mean, have some exact numbers. So in different theories, it's different. So, but still, I would like to show that this anomaly is important and can lead us to some unusual and striking results. Okay, so what is scale anomaly? Indeed, we know that very well, but let me just flash transparency and show how it works. So basically, we start with the classical theory, massless Dirac fermions interacting minimally. We know that scale anomaly, scale symmetry corresponds to invariance of the action and classical equations of motion under a global rescaling of the system. And on the quantum level, one gets renormalization, theory is renormalized, and electric charge is renormalized. So it means that it depends, the electric charge is different for particle interacting with different energies. And that's why one gets non-zero beta function, which corresponds to running of the coupling, how it depends on the energy scale. And in QED in particular, it's non-zero, less than many other theories. So theory gets conformally broken and the quantum level. And in the simplest case, how we could describe this in textbook, we say that, okay, we have electric charge, test electric charge, you put it in the vacuum, and then vacuum fluctuations appear from the vacuum, and just particles, positron electron particles appear from the vacuum, or say electron hole appear from the condensed matter vacuum, and they screen the particle due to just electric dipoles. And therefore, in particular, yes, the charge, even if you look far away from the charge, so for example, if you consider scattering experiment, then if you scatter far away from the charge will be smaller, and closer to the charge with higher energy, then charge will be bigger. So that's why this, when we have positive function. Okay, so, and actually, I would like to hear the quote. There is some experiment where the QED beta function was measured here. It's actually was running of fine structure constant and fundamental QED, and it's more or less well described by the theory. So that's standard picture of the renormalization of the charge. And then I would like to say that the same phenomena, of course, happen also in the condensed matter context. So right now I speak about normalization of the charges. We heard right now about talk about Kondo effect. Here is a different application of normalization group. Of course, there are many of them. So here we consider topological insulator, which is basically QED. It's QED, massive QED. I believe it's supplemented with the fact that we work in the crystal and not in Lorentz invariant vacuum. So we have here speed of light, which describes part of interactions, and we have also Fermi velocity. So it enters Lagrangian, and we have also Fermi velocity here and here, which says that our fermions propagate with the velocity of light. Maximally attainable velocity is velocity, not velocity of light, but VF, which is again 300 times smaller than velocity of, in the vacuum. And due to the fact that velocity of light is different from velocity of fermions, those quantities start to run due to normalization effects. And this effect was found first in the condensed matter, in the field theory context by Kostelecki group long time ago, and then it was rediscovered in the context of condensed matter physics in those two papers 10 years later, approximately, and later again. So it means that the Fermi velocity start to run. So it depends on the scale. So here is written logarithmic scale is distance scale. So here these are short distances, these are long distances, and we see that as we go to larger distances, then effective electric charge. This is how electric charge runs, goes down. So this is effective electric charge. So again, we have screening due to appearance of the pairs, electron-positron pairs from the vacuum. On the other hand, we have also running of the velocities. So Fermi velocity gets up, so it becomes bigger, while the velocity of light becomes smaller as we move to larger distances. Therefore, in infrared limit, we have infrared fixed point where in terms of velocities, there we have charge goes to 0, so it becomes 0. We have 0 point because we have total screening since particles are massless. Oh, by the way, here I consider massless particles. Yes, it's written here. There is no mass here, so I know mass is here. So here in this particular case, I consider massless particles. So we have 0 charge at very large distances, and also the system becomes totally restored in terms of velocity. So it becomes totally Lorentz invariance. But this is really, really far away. So, and to the system, similar effect was found. The only thing that there the Fermi velocity runs while the electric charge does not. So, and that was found also like 30 years ago, approximately 25 years ago, a little bit more. And the this effect of running of Fermi velocity, it's quite similar to this one, was found experimentally in graphene. But I'm not touching here graphene systems at all. I'm going to discuss effects which are related to with the renormalization of this part of the renormalization of velocity of electric charge. So electric charge goes down as we move to just to larger distances. Okay. So the statement that main statement of this talk will be all the fact which was discovered long time ago by McCavity and Osborne. It was discovered in this paper 30 years ago in somewhere in appendix C5, as far as I know, this first appearance of this effect in specific notations, which we translate to notations in this talk. They will look like this. So we will get that electric current. This is electric current. Here there is some coefficient. Here F mu is field strength tensor. Oh, yes, field strength tensor of electric field. We assume that we work at background field. And then this effect is written at the boundary. So we have a boundary, and if we have the boundary and applied electromagnetic field close to that, I will specify electric and magnetic later, separate them, we will get some electric current induced. So this is basically translation of this formula to the modern language, basically. And here n is the normal vector with respect to the boundary for vector, and x is the spatial distance from the boundary. So we assume that we have a boundary and fermions gets reflected from the boundary, get reflected and get back. So, and this x is interesting because it's needed from the dimensional point of view, because we must have the, we don't have any dimension full parameters except for the distances. So it must be here. So the current must be divergent. And yeah, that's all. And it appears if we put reflective boundary in the conformally invariant system of charged particles. And the relation to beta anomaly has been found recently, 3 years ago, by Chu Miyao, and published in those papers, and Jehep and Pirel. And we found recently, a bit later, numerical evidence of this effect, because to me, it was totally ununderstandable because 1 over x looked very strange. I could not believe that current is divergent at the boundary because we have a boundary. So it should be kind of strange, I would say. So this effect should not work because we need to have some finite value, and here we have infinite. But still, we recovered the effect, and I will talk about this a little bit later. And the application of this effect in condensed matter system has been described in our paper with Maria Vesmediano again 2 years ago. And that will be actually, this work will be the subject of my talk mainly. So let's discuss how we can understand how boundary can affect the scale invariance and can have something to do with scale invariance in terms of normalization, how it works physically. So it should be understood in the following sense that if we have the bulk, we work with the bulk, we have no boundary, then electric charge is renormalized just freely, in the sense that from any direction you can see the particle which appear, disappear, according to Heisenberg principle, and they form the electric dipoles which screen, and this screen is geometrically not reduced just because we have particle in the bulk and there is infinite space around. Once we put reflective boundary, now we see that the part of the charge is not reduced. It's just geometric effect. So the number of particles, which can appear from the vacuum on the right-hand side is bigger on the left because there is simply no space for the particle to appear. And that says that the current, or better to say the charge, close to the boundary, effective charge will be stronger than the charge outside of the boundary, far away from the boundary. So that's why there should be some effect. So since charge is different, it should affect somehow physics. And let's discuss it, how it will affect physics. So first of all, let's consider the case when we have only magnetic field. So here we assume the boundary which goes outside of the plane, and so out of the screen. Here n is a three-dimensional vector which is normal to the screen. X is the distance to the point where we measure current, and B is magnetic field which is tangential to the screen. So if we translate this law to just three-dimensional language, we will get that due to the boundary, one gets the current which is proportional, which is perpendicular to the normal direction to the boundary and to the magnetic field. So it looks like typical Hall effect. In a sense, the only thing that, okay, Hall should be taken in the brackets actually, yeah. Or yeah, so because it's effect due to conformal anomaly. There is no topology behind it, so it's not like in Hall effect, so it's not quantized, and there is no matter here because I did not put any chemical potential, and it also works at zero temperature, and it includes H, so it's a purely quantum effect, and it's related to anomaly, conformal anomaly, or better to say scale anomaly, because it has beta function. So it's unusual and quite, you just get current from nothing. And the example, another way how to understand it, that's simple in this sense. It's like the Hall effect in the system, conducting system, where the carriers experience no impurity scattering. So basically we have ultra clean limit of some material, and then we see that if, for example, we have a particle which is created, say particle antiparticle, say electron or hole, or you can think about electron positron, which are created in magnetic field. They form those circular directions, cyclotronic directions, and if they move in this direction after creation, they will very quickly annihilate according to Heisenberg principle quite soon, interacting with each other again. So just they move and interact. However, if at the creation they move at a little bit different directions, say parallel to the boundary, then at some point they will fill the boundary and will start to scatter. They will start to scatter unless they interact with some other particle. So, but in any case, you will see that as we move closer to the particle, to the boundary, you'll see that there is a chance for the particles not to meet each other because the boundary is reflected, and that's why we'll get the current. So negative charge will move in that direction, so to the left, and positive current will move in the right direction. That's why we will have no net mass transfer, which is clear. On the other hand, we will have double current transfer because left and right hand particle, the electric positive and negative particles move in opposite directions. That's why boundary in the presence of magnetic field should induce the current, and this current must be dissipationless. So it is similar to the Hall effect. However, we have no mass and no temperature at all. Okay. So we did not believe this effect. We thought that it's probably not correct, and we made a simulation. Fermions, we did the first principle simulation of the lattice. Fermions are hard on the lattice, especially massless fermions. So we found the conformal point for 3+1 dimensional scalar electrodynamics. So basically, we took a Abelian Higgs model, put potential to 0, mass to 0, found the corresponding conformal point, and we found that indeed that there is the current which is generated at the boundary. And this current, we put a Dirac boundary here, and we will see that, I should say that magnetic field is directed towards us with respect to the screen. And electric current is generated to the left and to the right as predicted by the theory. Moreover, the coefficient in front of that current, so this is current which is parallel to the boundary, and this is distance from the boundary in lattice units. This current, once we move to the conformal point, corresponds exactly to the prediction which is given by the theory. So we get 1/r. So it can be seen actually from this picture if you look carefully. So this is conformal behavior for massless scalar, and the coefficient in front of it is corresponding just to one loop beta function, which appears in scalar QED. This beta function is 4 times smaller than beta function in usual massless QED. Okay, so we have the current which appears at the boundary, and it has no quantization at all because it appears. It's governed by beta function. There is no topology behind it. Now let's come back to the integer Hall effect, because you know that in integer Hall effect, you know that electron, this coupling nu is measured with extremely high accuracy, and it's effective basically number of occupied Landau levels in the system. I'm speaking right now integer quantum Hall effect in this case, and this number is integer, and the fact is that this number is integer. Why it was found integer? Because it was there is. We can ask why there is no effect, normalization effect, which I talk about. Why it hasn't been found here. The reason is because those effects which were found in semiconductors, which are relativistic quantum mechanics, where you don't have relativistic normalization effects, and it was also found in graphene, where normalization exists. Of course, we have normalization. Electric charge. However, this charge does not run, electric charge doesn't run with energy scale. Okay, so that's why quantum Hall is well quantized in graphene, for example. Now let's consider scale magnetic effect at the edge, what it will give us in terms of the this quantum Hall. First of all, I must say that this is magnetization current. So that's why we have, in order to measure that, we need to measure really magnetization. So it means that this current cannot exit the medium, because it's basically given by virtual particles, which circulates. And contrary to the usual Hall effect, it's another reason why it can be so easily measured. It cannot exit the sample, so we cannot feel it so easily. It's one thing. However, it gives some important contribution. So this current, if you calculate the number which appears, how big it is, it becomes quite big. This correction comes approximately, if one puts all numbers, say permittivity and Fermi velocity, which appears, by the way, downstairs. So it enhances because velocity is smaller than velocity of light. So velocity of particles is smaller than velocity of light. That's why it will drastically enhance this effect, which now comes into strong coupling regime, basically, where actually beta function can experience some non-trivial corrections, by the way. And we get 5% correction, which is very, very well noticeable, and it's way above 10⁻10 precision measured in the Hall effects. So we must have some contribution from this vacuum effect in the Hall effect. So there should be some contribution from normalization to the magnetization currents which run around the sample. Okay, that's one thing which I wanted to say. And another one, you can ask, okay, so what? It's difficult actually to measure magnetization currents, because one should really measure some magnetization. It's not transport current at all. How can we apply this effect? How can we measure it? How can we understand it? Okay, then let's consider it a bit different point of view. Let me repeat, we consider it spatial components of this law. So we put here mu equal to 1, 2, 3 spatial components. Right now, let's consider temporal one, where mu takes 0, and then this J mu becomes charge, electric charge, and other components, they collapse and actually create here this product of n, which is n is again, it's the normal to the boundary, and E is electric field with respect to the boundary. So we'll get some charge accumulation of the boundary, which is governed by beta function of the theory, and and which should be accumulated. You see, it should be exploding at the boundary, at the edge. Okay, so can we see any effects of those, any experimental signature of this effect? First of all, let's consider the screening. Since we have charge accumulation, we can say, okay, there should be something to do with electrostatic screening here. Now let's think about metals. So we know that there is electrostatic screening in metals. And how it works, okay? We have basically two different quantities which characterize them. There is the Debye screening length, and there is Fermi-Thomas length, which here is more to electrolytes or semiconductors. This one has a relation to usual metals. So there are two screening lengths, and those length parameters, they say how fast the electric field, static electric field, decays inside the conducting medium. And in typical metals, say in gold, this quantity is extremely short, extremely small. It's a few nanometers. I think in gold, it's 3 nanometers. That's why people talk not about distribution of charges like 1 over like exponential, but better they talk about the surface charge, because it's a very, very thin surface charge. And in electrolytes, it can be a little bit bigger, but still this behavior exponential. So charge, electric field decays exponentially in the conducting medium. And both of those quantities, they are related to the presence of the length scale in the material. In our case, again, we have no length scale. So classically, there is no length scale. And therefore, there should be screening, because we know that there is some charge accumulation. So there must be screening. On the other hand, it shouldn't be associated with any screen. And as in many conformal effects, we already heard about that. The screening is actually governed not by the, it's governed by the length of the system itself. So to find the relevant effect, we can, but here actually, again, about interpretation, how to interpret this effect. This effect actually has also something to do with field theory. It's an analog of Schwinger effect, because when we apply electric field along the sample, so here let's put the boundary, and here consider the coordinate from the boundary to the sample, the electric field creates pairs. It creates positive electron pairs in field theory or in fundamental theory. In the condensed matter, we are talking about electrons and holes. Those pairs are created by electric field, and they tend to move in opposite directions, of course. Some of them annihilate, so some electrons and holes meet together when they annihilate, but usually annihilation rate, recombination rate is not so high. So what happens then, we get some accumulation of charges at one boundary and then another one. And this is the analog of the Schwinger effect, however, in the medium. And since the system is massless, there is no Schwinger gap. So there is no Schwinger critical field. So this effect happens at any field, even at smaller field, this effect will happen, of course, in an idealistic sense. So, so then since we have this charge accumulation, we know this formula, again related to beta function, we can plug it into the Maxwell equations. Let's speak about simplest case. So we have just Maxwell equations, which says that divergence of electric field is given by proportional to the density of electric charge at each point locally. And then we see that if we solve this system at the equations, so two equations, one come from conformal or scale anomaly, another one come from Maxwell equation, we can solve it, and we can see that the electric fields and charges and electrostatic potentials, they get some definite form, and this definite form the boundary will be like that. So electric field will fall down like x to the power nu, where nu is the conformal screening exponent. That's quantity which is given by a combination of beta function associated with renormalization of electric charge and some dielectric constants here. One can put here the dielectric constant of the medium. But anyway, it will be proportional. It's given by the beta function. Okay, and the interesting thing here that electric field itself is difficult to measure, and density probably is not also simple. But what is simple is to measure the electrostatic potential. It's what you do, you just take your medium. So in this case, we consider Dirac semimetal, put it into the capacitor. So just to induce electrostatic field, and then take the voltmeter and just measure the electrostatic potential at some distance. And since if the effect is polynomial in nature, so here is just electrostatic field depends polynomially on this coefficient nu, this effect is long ranged. So that's why it's much easier to measure that than the, say, typical screening effects. Those effects which will run on the scale of micrometers, which are quite manageable right now. And it turns out that the density, here is written typical behavior for the finite size material. Think of a Dirac insulator, Dirac semimetal. So here is electrostatic potential, how it looks like. So in the case of if we have no material and no screening, if this coefficient nu is equal to 1, then we'll have here some just line, which will be kind of quite simple. Okay, and we see that electrostatic charge density electric charge density appears due to external field. That's how the anomaly, conformal or scale anomaly could work in the Dirac material. So, and this thing is this quantity is accessible experimentally in principle, because if you put real numbers, then we will get that since Fermi velocity is quite small, it's here is an error. It should be it's approximately, it's really, sometimes it's 10 to minus 3, sometimes it's 1 over 300, so it's a matter of factors of order of 1 or 3. This conformal exponent, critical exponent, can be of the order of 10%, so 1 over 10th. So in principle, it can be measured. And here, for example, is shown the behavior in logarithmic scale of the potential as the function of the distance from the boundary of the material. And we can see that indeed the conformal anomaly changes the behavior quite significantly. So it could be also an evidence of the elusive Schwinger effect, also in condensed matter setup, but for massless fermions. And in this case, we will get the normalization of beta function associated with normalization of electric charge. So I am coming to the end of the talk. I think that I'm a little bit accelerated, so I was a little bit faster than I should. So we have the systems. We have simple system, the Dirac semimetal. Okay, it's not so simple, but its long-range properties are can be captured by simple Lagrangian, which is very similar to the field theoretical Lagrangians, which we used to describe in QED, albeit with a small mass, zero mass. Then those effects, the normalization of electric charge leads to the boundary effects, which are related to the polynomial screening of electrostatic fields. So we can get charge accumulation. And they are also related beautifully to the particle creation via Schwinger effect, at least can be interpreted in that way. Then those effects can be measured experimentally, in principle, because nothing prevents from that. The only thing that we should really be in exact conformal point, that's the only problem. So they can maybe measured as the property of the behavior of the electrostatic potential as a distance from the boundary. It can be, those measurements are done. And the scale magnetic effect, so at the edge, the effect which appears at the edge due to the running current, it leads to the edge currents in the absence of matter. They lead to non-integer quantum Hall effect. So those currents will run along the boundaries, and those will be magnetization current, but they will be non-quantized at all. And that's the difference between the normal Hall effect and this type of conformal effect, which leads to non-quantization of the current in the boundary. So I think that there are plenty of ways how we can get a beta function in this kind of clear tabletop experiment, which mimics the field theoretical QED. Okay, I finished.
Thanks, Maxim. We have plenty of time for questions. So if anybody, oh, Johanna has one.
Yeah, actually, I have two questions. So the first question is, okay, so you very nicely explained all these anomalies, and so you mentioned the fact that this particular conformal anomaly that you're looking at, well, okay, the beta function appears as a coefficient, and there's no non-renormalization theorem this is going to run. And then you said that you want to measure this beta function. Now, somebody from quantum field theory is immediately going to say, but this is a scheme-dependent quantity.
Exactly. Yes.
The killing argument of any quantum field.
No. You see, okay, that was the reason. That was the reason why we published this work. This work, because I said it cannot exist. It's just okay. I cannot say because it's recorded. Yeah. So I don't believe this. It does not work. Take the theory we have on lattice, and for us it was difficult experiment because numerical experiment because it was difficult not to measure the current, but to come to conformal point, because it's a second order phase transition. The lattice we have to have a big lattice numerical simulation, but we found the point, did it, and we found that current. So we were really surprised and said, okay, but look, this beta function is proportional to beta function. How can it be? What's about normalization theory? The point is the following. In fact, indeed, you have dependence on the scheme. It appears in higher loops, but in higher loops, the effect will be different. It will become non-local. That's my expectation. It's similar to what happens in principle in graphene. You see, graphene can also be considered like conformal symmetry, a conformal theory embedded into 3+1 dimensions. So photons can travel outside of the graphene sheet, but the physics of electrons is described basically by conformal interactions, with the only one correction that actually it will be immediate from the point of view of electrons, one-to-one correspondence between the points. So it will be 1 over delta, I don't know, immediate Coulomb interaction between two different points, because for
okay, so I understand. So you're claiming that only the one coefficient is a local term in presence of the boundary. Okay.
Yeah, and that's a very interesting question, because in principle one can extend it and look how this theory changes at large at large loops. Sorry, large loops.
Yeah. Okay. Okay. I have one other question. Can you show again your table of all the anomalies?
Table of what?
At the beginning of the talk, you showed a list with all these 3-point functions and.
Yeah, this one. Yeah.
Okay, I'm sorry. I wrote my PhD thesis about these things. So anyway, so I have one question. So in the diagram on the right of this table, okay, so in your anomaly at the bottom now, you have a local gauge field in your anomaly, okay, because there's the beta function.
Yes.
But in principle, you can also have a global. I mean, for instance, if you look at this the mixed anomaly, okay, so then this axial current actually couples also to a gauge field in the background, but it's not from a local gauge symmetry. I mean, it's a U1 field which is a source for this current.
Okay.
And in principle, the anomaly on the right, you can also have, if you just take derivatives with respect to the source of the current, not the dynamical gauge field that you show in this anomaly.
Okay.
So is there anything you can say about that, or why are you sure that you just have the dynamical gauge field there and not a kind of background gauge field?
Sorry, that's all background. That's background fields. Here R is gravitational background, F mu is background, and here is also background. That's classical background here.
But then are you sure that this is the beta function? The function then?
Yes. It should be seen. Yes, it's, for example, again, can I ask Lorenzo not to type or switch off somebody's typing and it's really kind of resonating a little bit here. Yeah, so switch microphone, switch off microphone. Yeah, okay. Yeah, so yes, it's really, that was really the case. Yes, that's an anomaly you apply here. Yes, you consider background electromagnetic field, and it should be a classical field. Those fields, they are classical, and this anomaly is different from that one because it's not one loop exact, and it also should be understood, in terms of, it's not operator relation. It should be understood only in terms of expectation value of matrix elements. That's why it's less beautiful than those ones. So it's
okay, but then maybe this beta function is a bit different from the beta function of QED.
No, I don't think so. No. There is no.
Okay, I need to think about it. Okay, thanks a lot. But, yeah, okay, thanks. So you're talking about the global anomaly there. I mean,
here, for example, here conformal anomaly is global anomaly in the sense that it's weighted on. That's why I stress it. It's really scale anomaly. It's really scale anomaly. There are some particularities when we consider Weil anomaly and we consider conformal anomaly. There are some particularities, but here we consider only scale. We say conformal because in 3+1, most those notions coincide in practical reasons. If you consider, then all local theories which are Lorentz invariant and so on, with some specific symmetries which we usually ask to obey for field for variables from the point of view of field theory from phenomenology. Then those two notions are basically in practical level are the same as far as I understand.
Yeah. Okay. Yeah. Okay. I would just say, sorry I will stop in a minute. Just one quick thing. I mean, the thing is that this is now a beta function, but if you really have a global anomaly, this the anomaly will also be there at the fixed point. So I'm not really sure this is the same as in because if it's the running beta function of QED, it should vanish at the fixed point. But there's also an anomaly, a conformal anomaly at the fixed point which persists even if the beta function vanishes. Okay, I'll send you my PhD.
You're talking about just 1 second, because it's there are a few notions which look similar, but in fact they're different. You're talking about Wilson-Fisher fixed point?
Just any conformal fixed point. If you just have a conformal field theory where the beta function vanishes, you can still have an anomaly of this type, although the beta function is zero.
Yes, but then you will not have this effect then. Then you have the effects which I discussed will not be there. That's all.
Okay, so, I have to think about it, but maybe I can. I will send you my PhD.
Yeah, because if you're talking about this point, this actually for me it's fixed point of departure. You know, I mean, if you talk about this one,
Yeah.
I'm talking about, of course, you can consider, for example, massless theory. If you consider massless theory, as I discussed, then indeed, if you look to large distances, infrared distances, then of course electric beta function will vanish by definition. But that will be completely in agreement with this formula, because beta function divided by E is E squared, and E vanishes. It will be this zero charge effect. Which theoretical, okay, applied physicists, okay, people who study, for example, in, I don't know, any example, say helium-3. In helium-3, there is this effect when effectively you can consider some effective charge which vanishes at large distances. And then you will get also a similar effect, and this effect will be a zero charge, and this term disappears. Fine.
Okay.
Okay, we can probably discuss later. So maybe.
Yeah, thanks a lot. Yeah, thank you very much. Thanks for the nice talk.
So Johanna, if you're in the discussion session, we can.
Yeah, okay.
So Renee is next. Sorry, you need to unmute.
Hi, thanks for the nice talk. Nice to see you again.
Yeah, nice.
So maybe I had a comment on what Johanna just said before, but maybe I will keep that for the discussion session about the scheme dependence. But so I have two questions. First of all, this anomaly there, so the trace anomaly that you find, is that topologically protected? And second of all, that's kind of related, like how stable is this under realistic conditions, including impurities, roughness of the boundary, and stuff like this. So in principle, you know, I keep on talking to these condensed matter people like Evelina, and in principle, everybody's telling you when you come up with a new formula, oh, you should do like a microscopic, whatever, kinetic theory calculation to confirm all these issues. Yeah. So. Yeah.
Yeah, first of all, it's not topologically protected. It's not one loop exact. So we don't have any beautiful things like, for example, like Berry phases and those Chern numbers. No. This anomaly is, in that sense, is dirty from the point of view that it's, there is no protection basically. So no bulk boundary correspondence, at least naively. Okay, there is, for example, the bulk effect, bulk scale magnetic effect. You can also find similar magnetization current in the bulk, not at the boundary. That's why, so you can say that there are two similar effects, but I'm not aware of about any topological physics behind this particular conformal anomaly, because it's next loop you get another one, and so on. So it's not in a sense.
Sure.
Yeah, okay, about impurities is better for discussion session, but let me mention that impurities, they usually break, okay, at least naively they break a scale, because you need to put some density of impurities. So this effect should be done in ultra clean limit, like for example hydro is done. So you need to have ultra clean system. So yeah. Yeah. So particles should interact with the boundaries and with themselves at shorter distances than they interact with anomalies or with phonons, because you can also ask about phonons here.
Yeah, exactly. Yeah.
They're even worse. They're even worse than impurities. Okay, at low temperature, of course, they can be neglected, but depends on.
Yeah.
So it should be ultra clean, zero temperature, zero chemical potential.
And then you say, okay, so if these conditions are met, you say there might be 5 to 10% deviation from the quantized conductivity for, let's say, if you would make the sample rather small or something like this. Is that what you're saying?
Yeah, you see, but the size of the sample doesn't matter, because effect is logarithmic. The difference between 1 micron and say 1 kilometer is very small. I mean, in terms of logarithm, it's basically the same. Here you see it's infrared, ultraviolet.
I see.
Additional factor 2 pi, for example, doesn't matter. The worst thing here is not that. The worst thing is that it's magnetization current. It cannot exit your sample. You see, so usually what you do with hole, you just take, for example, let me come very quickly back. Sorry for this. What you do with the hole, you usually take this whole geometry, you put here magnetic field. Here's ultra clean limit. So we So we put here, if we have no electric field, then we have here one current runs up, another one runs down. Somewhere they get closed, and that's why nothing comes out. That's all, just pure magnetization current.
Yeah.
Then you need to introduce, you need to put here electric field. An electric field will create here chemical potential, which is positive, for example, here chemical potential, which is negative, and you will have some kind of difference between particles here and say holes there. So it will be kind of, there will be difference between particles which are going up and particles going down, because electric field creates difference in chemical potentials at both sides. And that's why you get current, which is perpendicular to magnetic field, which is out of plane, and electric current. And that's electric field, electric field and electric current. So electric field, magnetic field, electric current will form triangle. Okay, triple system, I mean, just, perpendicular one. So that's how it works. And here, all particles are virtual. So they don't appear, you don't have any chemical potential. And that's a problem. So you can only measure them using some magnetization. Yes, some magnetization, some experiment when you put, for example, this diamond with some impurity inside, and you look very, very close to the edges. And that is possible. It's possible. I know that the resident group did it, and in principle, but of course, one should really be very, very precise, because the difference is 5%. It's actually a mild estimate. In principle, one can have bigger. I'm just afraid to put bigger number there, but it could be much bigger. But only in terms of magnetic field, because it's magnetization current which cannot exit the sample.
So in the interest of time, let's go to the last question, which is Christian.
Hey, Maxim, thanks for the nice talk.
Thank you. Yeah.
Hope you're doing well. So I was just wondering, so I believe, I'm not quite certain, I never worked on this, but
in static background, they are very well known, and they are given by some numbers for one fermion. If you have other degrees, they're given basically by central charge, by degrees of freedom on your system. And then you can get the current here. So you get the current which will be non-local. Sorry, I flash transparency because I don't have time. We can discuss maybe my discussion session, but it will be non-local. It will be this fourth order Pani's conformal differential operator, but they can be written in local terms. And if you again, I flash very quickly. If you come back, it can give to Nernst effect. It can give rise to Nernst effect, which will be proportional to beta function. So you'll have bulk effect, which is analog of the effect which I discussed on the magnetization current at the boundaries. But here will be bulk effect, and it will be also proportional to beta function. It will come from gravity part. Okay, from basically, okay.
Yeah. Well, we'll come back to this in the discussion session. But right now, let's thank Maxim again.
Thank you.
And then stop the recording. And we will meet again.